So welcome, everybody. Thanks for joining this session. Today, I will be talking about the quick compiler in Art, the new Android runtime. So first of all, I want to give the motivation behind this talk. In the last couple of years, I've been working for ARM on a very interesting project. We were basically making sure that Android was running well on our new 64-bit architecture, ARM v8. And this project was interesting and had interesting challenges. One of the challenges I was mainly concerned with was working on Art and its quick compiler, and making sure that the quick compiler in Art could generate code for the new 64-bit instruction set in ARM v8, which is called A64. So this was an interesting journey, and we learned some things in this journey. So today, I thought I have a good opportunity to share some of these with you. And the hope is that I will generate some useful information in case any of you guys will have to work on Art in the future. Before continuing with the presentation, I'd like to point out that this presentation represents my opinion, my point of view, so it doesn't represent in any ways the opinions or point of view of other people, like Google, for example. So it's my take on it. So the presentation is subdivided into three parts. The first part is the bulk of it, is the longest part. And I will, in this first part, take a very simple Java program and show how you can use Art to run it. And then I'll have a look at the assembly code generated by the quick compiler in Art and take this output as an opportunity to view some of the features of Art. In the second part, I will then move to exploring how the Art quick compiler works, quite briefly, how it is structured internally, and then explain what, in my opinion, are the good, what is good and what is bad about it. And finally, in the third part, I will show some of the generated code from the Art quick compiler and go through it and discuss it. So let's start with the first part. First of all, what is Art? So Art stands for Android Runtime, and it is a fundamental component in Android. It is the engine which executes the applications written in Java. In Android Lollipop, Art is the only way, the only runtime available to execute Android applications. And for the first time, it replaced Dalvik, which was the default runtime in previous versions of Android, like KitKat. Art aims to be compatible with Dalvik in the sense that it starts from the same input files, the APKs, the Android applications, but it works differently. So the input is the same, but it does things slightly differently internally. There are a number of differences between Art and Dalvik. There are two that I'm mainly concerned in this talk. The first one is that Art introduces a 64-bit mode of execution. So it has two interpreters, two versions, one which is 32-bit and one which is 64-bit. And the second point is that Art introduces ahead-of-time compilation. So this means that while Dalvik was used to basically provide a virtual machine which was executing the applications, and then it had the just-in-time compiler, which was observing the execution, finding the patterns which were more frequently executed, and compiling these just-in-time. Art works differently. So with Art, you have ahead-of-time compilation, which means that at the time of installation of the application, it gets, the APK gets converted into a node file, which contains native executable code. And when then the application is executed, this auth file, which is cached in a directory, is used to run the application. So auth files are special types of ELF file, and later in the presentation, we'll see the content of them. So let's have a look at how we can take a simple Java source file and execute it with Art. So what we are doing here is rather different from what would be normally done by like an Android user. An Android user would use the Google Play Store. But here, really, we are interested in understanding how Art works internally. So what we'd rather do is use Art as a command line tool, sort of tool, right? So we start from a very simple program that prints the string out on the screen. And then the first thing we do is we compile it using an ordinary Java compiler, Java-C. And this takes the Java source file and gives a helloworld.class file, which contains Java bytecode. This is done on your host machine, and at this point, however, you need to convert this Java bytecode into something that Android can understand. And for this, you use the DX tool, which is an Android-specific tool, which is provided by Android SDK, which takes the Java bytecode and spits out the Dalvik bytecode, which is another sort of bytecode. And here we name this file helloworld.jar. So at this point, we have the bytecode, the input that Android can understand. So we need to now push the file into the device. And for this, we use another Android-specific tool called ADB. We connect to the given IP address of the Android device, and we push the file into a chosen location. In this case, data/user. At this point, we use, again, ADB to connect to open a remote shell to the device, enter the location where we put the file, and use the command Dalvik VM64 to launch execution. And what we get is the expected hello world message in here. So there are two things I would like to notice at this point. So the first thing is that we have a 64 suffix to the Dalvik VM command. And this is used to select the 64-bit version of Art. If we used a 32-bit suffix here, we would be using the 32-bit version. So we have two versions of Art, and we can choose one or the other to execute pure Java applications. The second observation I want to make is that this is maybe a stupid observation, but this is called Dalvik VM64 rather than Art VM64. And this is because, as I said before, Art aims to be compatible with Dalvik. So it has the same interface, and it executes the same apps, but it does it in a slightly different way. So indeed, if you go into this directory, data/Dalvik cache/arm64, you'll find a file that Dalvik would have not produced. You'll find the auth file that I was mentioning before. Despite, indeed, this file doesn't have the .auth extension, this is indeed the auth file here, data@user@helloworld.jar, etc. So we'll have now a look what is contained inside this auth file. And in order to do this, we use, again, ADB pool. We retrieve the auth file from the location in the Android device and put it in our machine. And then we use the auth dump tool, which is another Android tool, to dump the content of this file. And we can see three things inside the auth file. First of all, we see these instructions, four instructions as get, object, const, string, invoke, virtual, return, void. These are Dalvik instructions. So we have the original Dalvik bytecode copied inside the auth file. The second element contained in the auth file is metadata. So if you have a look at the central part, the bottom part, if you want, of this slide, then you see things like float fp spill mask, core spill mask. This is metadata. And it is all this content is relative to this method, which is the helloworld.main, which was just printing the string to the screen. It's important to notice that Java is a managed runtime. So it has things like automatic memory management, garbage collection. So this means that the garbage collection at some point will need to scan the stack, make sense of it, find live objects, and collect like garbage. So this metadata describes what the method does and enables the runtime to do this to make sense of the stack when it's time to scan it. And finally, the third element contained inside a node file is the native code. And you see the last line here is like an A64 instruction, sub x8, sp, 2000. And I omitted here most of the native code generated, but I will return on this extensively later in the slides. Before doing this, I would like to have a look at the ABI for the quick compiler. So here, basically, I'm showing you how the quick compiler uses registers, the core registers. You have a table, and the way we are using register in the quick compiler is very similar to the ARM architecture procedure called standard for 64 bits. In particular, the first 8 core registers are used to pass arguments to the methods. W0 is typically used to pass a structure which describes the method which is being executed at the moment. If you have more arguments, you would obviously put them into the stack. Then the next register from 8 to 17 are used to hold temporary values. Register 18 is used for a special purpose, is used to contain the pointer to an object called the thread object, which contains useful information for the runtime. So the runtime will often use this register to access this object and access useful information in this object. There is then register 19, which is again allocated for a specific purpose, and it is allocated for suspend points, for suspend checks. We'll return on this extensively later. And then we have the coalesced registers. So these are the registers that are preserved across calls, and they are used to store the values that in the program, which are used more frequently. Finally, we have the link register, which is used for containing the return program counter. And for floating point registers, we have, again, we follow very much the AAPCS 64. So I won't now show a table here, but it's very similar. Another interesting feature for the quick compiler is that we are using compressed references. So you may remember I was saying that Art introduces a 64-bit mode of execution. This is a great thing, but you know that one of the main issues with this is that pointers grow from 4 bytes to 8 bytes. And this is, this is an inconvenience. It makes your memory requirements bigger. So one way to circumvent the problem is to use compressed references. So the idea is that you would use the bottom 4 gigabytes in the virtual address space, and the Java heap would use these 4 gigabytes. This allows you to basically safely truncate pointers to 4 bytes, and therefore you can store them at 4 bytes, and therefore circumvent the grow in the memory used by the application. Obviously, one price to pay is that per application, it can only use up to 4 gigabytes. This is actually quite a lot of memory for an app. And anyway, the native libraries can still use full pointers. So another important part of the ABI is how the stack is structured. So here you see the frames for 2 methods. The current method, which is in light blue, and the caller method, which is in dark blue. Now, I don't want you to understand everything about the stack in this hour. However, I'd like you to just take one message with you. The stack is really carefully structured in the quick compiler. We need to follow a protocol. As I said before, for garbage collection and similar tasks, the runtime needs to interpret and make sense of the stack. Therefore, we need, in every part of Art, to just follow some protocols to make sure that all the parts work properly with each other. In particular here, I noticed that there is this yellow-colored region which contains the values of the virtual registers, which are used in the current method. The stack will travel over the runtime will travel over the stack and will read these registers and will recompose the state and make sense of it. So it is important that we are doing things properly here. Another interesting part is the in and out region. Arguments, as I said before, are passed in registers, but we always allocate space for them into the stack. And we do allocate them into this in region, which is actually the out of the caller. So the out region of the current method becomes the in region of the next method. Again, I don't want you to understand everything, but just the main bits. So here we come to the main, to the method that, the Helloworld method that prints the string hello world to the screen. And we have a table. On the right, you see the assembly code generated. On the left, you see the description of the various blocks. So now we go through this point by point. So the methods start with a Stack Overflow check. So it is important in Java to be able to handle Stack Overflows in a nice way. You don't want the application to crash. So the first thing you do is the following. You take the stack pointer, SP. We subtract a value, which is 2000 in hex. And you get at the bottom of the stack. At this point, you do a load. And this load can have two outcomes. First is that it succeeds. Then we discard its value because we are using the 0 register, which in the A64 instruction set is used to discard values. The second possibility is actually that this load causes a segmentation violation. And this means that we have reached the bottom of the stack. So if we have a segmentation violation, then a signal is raised. And the runtime will understand that this is actually a Stack Overflow, that a Stack Overflow occurred. And then we will have enough space to raise a proper exception because we are not yet over, we are not yet out of the stack. We subtracted 2,000, so we are sure that we have a given amount to handle this exception. After the Stack Overflow check, we have register spills. You see that we are creating the frame by subtracting SP with a given value, the size of the frame, and then we are spilling the registers into the frame. Here we are spilling them in a particular location. Again, these values will be used by the runtime to reconstruct the state of the stack when a garbage collection, for example, has to occur. After the spills, we have that arguments are pushed again into the stack to ensure coherency again. So we want to keep the stack in order. So we either push arguments into the stack or we push them into collisated registers. Collisated registers, as I said before, are registers that are preserved across calls. So X20 is one of them, for example. After this, and again, this is the main purpose of this is keeping the stack in consistent state. After that, we have a number of instructions I cannot go through like in this limited time, but I would like to point your attention on a frequently occurring pattern, the fast and slow path. In this case, what we have to do is to print a string in the screen. And the first time we access the string, we will have to resolve it. We will have to do sort of a linking resolution. So we check whether the string is resolved. If it is not, we jump at the bottom of the method where we call a handler here. We call the runtime. The runtime will do the resolution, and then we jump back from here to the point where we call the resolution trampoline. So at this point, yeah, this is one of the reasons why you may want to use this slow path. But even if you, for example, have a division, you have to check whether, for example, the divisor is 0 or not. Then if it is 0, you have to raise an exception. And this would be the slow path. It's just another example that shows you how this can be used. Finally, we have another very important pattern, which is the pattern of suspend checks. Suspend checks, as you see, they are checks inserted into the code quite at appropriate times. Now, I will return on this quite extensively later in the talk, so here I'll skip describing them. Just remember that you see they are just instructions inserted into the code. And finally, we have the return statement. So before going into suspend checks, I would like to take a step back and explain what, in my opinion, are the design requirements behind Art, and what kind of implications this has on the design, on the implementation. Sorry. So first of all, as I said before, Java is a managed runtime, and this means that we need things like garbage collection, and this means that, as I said before, consistency is very important. Another requirement is that Android is targeting mobile devices, and this means that user responsiveness of the graphical user interface is very important. You don't want the animations to stop or being not fluid. You want things to go smoothly. So you want the garbage collection to have a low latency. You cannot afford having a garbage collection pausing all the threads for a second, right? So this is another important constraint that you have, low latency garbage collection. Finally, Dalvik, Art is compatible with Dalvik. It needs to provide features that Dalvik provided and to aid Android developers in their debugging experience. And for this, we need full speed debugging and profiling. In practice, the user needs to be able to connect to an application and attach a debugger and see what is happening without having to recompile everything. And this has an effect on what we can do in the compiler. We can optimize things, but we must be sure that profiling still works. And then we must allow things like single-step debugging or setting breakpoints from the debugger. And you can imagine that if you have a compiled application, and this is quite difficult. So one way we do this is basically through the optimization. So the optimization is a process through which you go from native execution to interpreted execution. So at some point, the runtime stops, parses all the stack, makes sense of it, translates into an interpreted stack, and then gives the control back to the interpreter. And the interpreter continues as if it was, just interpreted code. So these are requirements that, in my opinion, drove the way art is designed. And I hope that by considering this, you will be able to understand why suspend points are made in the way they are made. In particular, suspend points, which are also often called in literature save points or interrupt points, are a technique that has been in use for quite a while. So in this paper from 1992, you find quite a nice description of how this methodology works. And it's kind of a frequent methodology in Java. So what are suspend points? Suspend points are checks inserted into the generated code to make sure that the Java thread stops executing in a spontaneous way when they're requested to do so. So we are talking about cooperative suspension. There are also points of consistency between native execution, runtime, and interpreted execution. So in this slide, you see this line, which represents the execution of a native thread, like if a compiled code. And the suspend points are represented with these red circles. So you see that the compiled code is subdivided into intervals, which are separated by suspend points. Now, between suspend points, we can carry out optimizations and optimize the code. However, when we reach a suspend point, we need to make sure that the heap and the stack are in a good state so that the runtime can take over and run things like garbage collection or the optimization. So why are we using suspend points? And there are three reasons why we do this. I mentioned before. One is garbage collection. So at some point, you may have the garbage collection deciding to tell all the threads, do some work for me, scan your own stack, find the live objects, and so on. Or the garbage collection thread may say to all the thread, now stop, I need to take over to do some operations that require you to be sleeping. So garbage collection is one reason. Another reason why they are using Art is for profiling. So if you attach your profiler to a running Java applications, suspend points can be used to instrument the code. So basically, whenever you reach a suspend point, the runtime will record where you are in the code so that you can collect some profiling data, which will generate your final profiling report. Another reason, as I said, is for debugging. So at some point, while the code is executing, the debugger may say, now I want to start debugging with the interpreter. So at the suspend point, the runtime will take over, say, OK, I stop here. I go over the stack. I read the stack frames, which, as you may remember, they have a particular shape, right, a particular structure. And these frames are converted into interpreted frames. After this conversion happens, then the execution can start again on the interpreter. So you understand this is quite an involved process. So there are a number of reasons why suspend points are important, but now what are the requirements over them? So here you see like a simple case where we have a loop. The loop is represented with this arrow. Imagine you don't put a suspend points inside this loop. What can happen is that your thread goes forever and never stops. And you don't want this because you want low latency garbage collection. So you need to put a suspend points inside the loop to make sure that every thread can spontaneously suspend if it is requested to do so. As we need to put suspend points often in the code, they need obviously to be quite cheap because if they take a lot of time to execute, then they will degrade the performance of your compiled code. So now let's have a look at how suspension is done in practice. This is the way we do it for the x64 backend. So for the ARMv8 architecture. There are different implementation in Art. This is one. So for A64, we do as follows. We take a register, which is number 19, and we set it to a value of 1,000 at the beginning. Then when we reach a suspend point, we decrement the register by 1. And we have two cases. Either the value of W19 is greater than 0, and then we just continue. We don't do nothing. We don't do anything. Or we reach the value of 0. In this case, you see here, this is the sub instruction. We jump to a helper, to the end of the method here, and we call the runtime. The runtime will reset the counter to the value of 1,000, and we'll check whether the runtime has asked to stop the thread. If this is the case, then you could have a garbage collection, you could have the optimization, otherwise you just return back. And the return back then it happens at this point, and then we continue after the suspend point. You understand that before a suspend point, you need to flush all the register into the stack to make sure that the stack is in a consistent state. So we have seen quite a lot of things, quite a lot of material in this first part. I would like you to go home with a number of messages. First of all, you have seen Art introduced ahead of time compilation, and that consistency between the various parts of Art is quite important. And this consistency is achieved using a careful structure in the stack and using a methodology which is based on suspend points and the optimization. So we can now start with the second part of the talk. In this part, I will go quickly through the structure, internal structure of the quick compiler. I will later say what, in my opinion, are the positives and negatives about it. So first of all, Art was written to support multiple compilers. The quick compiler is one of these compilers, but in Android Lollipop is the only one you can use to run applications. It is simple, it is fast in the sense that it can generate hundreds of megabytes of native code in the matter of minutes. And it is derived from the Dalvik just-in-time compiler. So if you're familiar with the Dalvik just-in-time compiler, you will be familiar with the Art quick compiler code base. If you have been following the progress in AOSP for Art, then you will have seen that Google is working on a new compiler called the optimizing compiler. And ARM is helping with that for the A64 version. In the future, we can imagine that Google will either replace the quick compiler using this optimizing compiler, or complement it. We'll have to see what happens in this time. So now I will go through the internal organization of the compiler and describe the internal representation used by the compiler. So you see that we are starting from the Dalvik bytecode, which is the instruction we saw at the beginning. We will describe this later. And the final code is, the final output is auth files, which we said are special types of ELF files. And in this journey between input and output, we have a conversion into a number of intermediate representations. So first, we'll describe all the representation, then I'll describe how a representation is mapped into the other, the process of converting these representations. Before doing this, I would like to point out that in the quick compiler, the Java method is the compilation unit. So what happens when you call the Dalvik VM64 executable is that this internally calls the compiler, which is called dex2auth, which generates the auth file. And it does this by starting several threads. And every thread will compile one method after the other. So all the methods are sort of compiled concurrently, let's say. This is a good approximation of what is happening in reality. So let's have a look at the input of the quick compiler. We said this is the Dalvik bytecode. So the Dalvik bytecode is a register-based instruction set where instructions have variable length. They can, the minimum is 2 bytes, but they can be greater. The registers are called virtual registers, or VREGs, and they are 32-bit in size, and they are untyped. This means that virtual register can contain an integer, it can contain a float, And these registers are numbered from 0 to 65535. So we have about 65,000 of them. And if you need to store a 64-bit value, you would use consecutive pairs of these registers. So this is an example of a Dalvik instruction. If you are interested, you can go to this location, and you can find more about the Dalvik instruction set. The next representation is the so-called mid-level intermediate representation. In this representation, a method is represented as a graph made by basic blocks. And every basic block internally is a chain of MIR nodes. This representation is faithful to the input bytecode. So this means that every Dalvik bytecode has a corresponding MIR node type. There are, however, extra MIR nodes which are used for annotation purpose. For example, for null checks, you have an MIR node. And then also for optimization purposes. So there are passes that are using extra DEX nodes. The next representation is the low-level intermediate representation. So while the MIR was very close to the input, the LIR is very close to the output, very close to the target instruction set for the target architecture. And this in particular means that for every instruction in the target architecture, you have one kind of LIR node. And in this representation, methods are represented as chains of LIR nodes. The LIR nodes are sort of instructions, so they are chains of them. And you have extra LIR nodes, which are used to represent things like barriers, for example. So if you want to have the concept of a barrier where which delimits the code where you cannot, puts a limit to where you can push loads, for example, then you would use a pseudo LIR. As we have several supported target architecture in Art, we have several different enums for LIR nodes for ARM, R64, x86, and MIPS. And here you see how in the quick compiler you would generate one of these nodes. This is a node for the move W0, W1. The final representation is the actual output code, which is the auth file, these auth files are cached in this directory, as we saw before. And as we discussed before, they contain three things: the input Dalvik bytecode, the executable code, and the metadata. So now let's see how MIR, like the Dalvik input file, is parsed in order to construct an MIR graph. So this is done by parsing in sequence all the Dalvik bytecode. And then when branches are found, or branch labels, these blocks are split so that you get basic blocks. And they are organized into this graph of MIR nodes. Once a graph is built, then several passes are made, like SSA, type inference, redundant check elimination. And there is an engine that manages all the passes. So once the MIR graph is completed, we have another step, which is register promotion. So basically, we scan the MIR graph, find out which virtual registers are used more frequently, and then we assign these registers, this virtual register, to physical register. In particular, we assign them to collisate registers, which are those registers that are preserved across calls. Once this is done, once this assignment of registers, of physical registers, is done, we are ready to translate MIR into LIR. So this if you look at the code, looks very much like a loop over a loop containing a big switch statement. For every MIR node, you would call a different function which translates that MIR node into a sequence of LIR nodes. And once you get the final LIR chain, you do some extra optimizations passes like load hoisting and load store elimination. Finally, some fix-ups are done depending on the range of arguments. Some instructions are chosen rather than others. And then branches are resolved, branch target, branch offset are resolved, and also global method branches are done. And finally, the translation is done into the output auth file. So here I give what, in my opinion, are the positives and negatives about the quick compiler. So if you have a look at the Google I/O presentation, you see that actually Art is typically faster than Dalvik. And it is a very quick compiler indeed. So as I said before, it can generate lots of compiled code in little time. The negative, in my opinion, is that LIR and MIR representation are chains of nodes rather than dependency graphs. So things like doing code motion, detecting dead code, or like peephole optimization, like replacing sequences of MIR nodes with particular instructions, are quite difficult to do. Also, MIR and LIR are quite different from each other, so if you write an optimization on one representation, it won't work on the other. So there is kind of a hassle involved in having these two representations. So now I'm ready to go into part 3 of the presentation. In this case, I will take a very, very simple Java method. It's just a method taking an integer as input and giving an integer as output, doing a very simple computation. Here you see the 4 bytes code that are generated from this method. You see that the value x is passed in the register v2. We sum 1, we increment it by 1, and we store it in v0. And then we compute the square of it, we store it in v1. And then we sum them and return the result in v0. So this is the Dalvik bytecode. You see it at work. Now let's have a look at what code is produced by the quick compiler. So here we see the A64 assembly, and you see that it's actually quite a lot of code for this small fragment of Java source. And being a very small method, this shows you all the overheads are involved at the moment with the quick compiler. If you have a look into the assembly code, you see that only 3 of these instructions are doing the actual computation. But there are lots of other instructions that are, again, the overheads, which we will discuss now. So first of all, you see that the method begins with allocating the stack frame and then spilling registers. This is, in a way, a bit strange because it could be strange from your point of view because this is a leaf method, so you may wonder why are we allocating a stack frame. We could do without it. The fact is that we are actually, even if this is a leaf method, when we compile it, it may result not to be a leaf method because we may have to call the runtime to implement certain instructions, for example, certain Dalvik bytecodes. Okay. Next thing, we see that after the spills, we push the registers either into the frame in the stack, or we put them into a call-saved register. The registers that are preserved across calls. And this is, again, to an overhead which is in the attempt of keeping consistency at every point. And finally, you see a suspend check. So we have seen before why suspend checks are used. And here, if you omitted the suspend check, then you would not be able to detect this method in profiling. So you actually need to put a suspend check if you want profiling to work correctly. So this is, as you see, is quite a lot of overhead. Considering that, in a way, this suspend check will trigger quite rarely, right? Because if this counter is set to 1,000, it will trigger once every 1,000, but also less than that, because the runtime may not have requested suspension. So the problems here is that, first of all, we are doing excessive spilling, and this is because of the tendency of the quick compiler to use call-saved registers. Here, as this is basically a leaf method, you would not like to use call-saved registers. Call-saved registers are useful if you are calling a lot of methods because they are preserved across calls. Here, probably we should do a bit without them. The second problem is that we are paying a cost for the stack maintenance, and we pay this cost every time, even though in principle we only need it when we are doing a suspension. So possible improvements in this particular case is inlining. If we did inline this code, then we would not pay all these penalties. Or at least we would share the penalties with the caller. Another possibility in this case would be the following. At the beginning of the method, we could check whether a suspension is requested. If it is requested, then we use this version of the method. But if it is not requested, then we could just use a smaller version which just does the computation and returns. So this is a possible way of improving this method. So this brings me to the summary. First of all, I'd like you to bring home a few messages. So first of all, as we have seen, Art introduces ahead-of-time compilation. It is compatible with Dalvik, but it adds a 64-bit mode of execution. It gives a significant performance improvement with respect to Dalvik, despite there may be further work to improve it. And then, in general, it gives a framework which is easier to extend with respect to Dalvik. It supports multiple compilers. It makes adding new GC schemes easier. And finally, we have seen an important point, which I repeated many times in this presentation, that consistency is quite a crucial point. And if you are a hard developer, this is also one of the main issues you'll find. So when you write the compiler, you have to make sure you don't break anything. And this is actually more difficult than in other kind of compilers, I guess. And you find here further readings if you are interested. And now I'm ready to take your questions if you have any. Thanks. Sure. Thanks.
So, given that Java virtual machine is a very special kind of application, did you consider, and from your presentation, it seems that compiled code more or less follows standard Linux ABI. Mm-hmm. So same same set of color-saved registers versus color-saved registers. And did you consider using a different ABI, maybe changing ABI on the fly in the virtual machine, so that the compiled code will be more performant?
Yeah, this is actually an interesting question. At the moment, we are sticking with the ABI. The current ABI, but it is true that, for example, we have temp registers are maybe too many, considering we have like you know, from 0 up to, is it 17? But at the moment, we haven't really considering changing it, also because Google is working on a new compiler, like the optimizing compiler, and it's likely then that it will make better use of this. So at this point, I think it's a bit, you know, not the right time to do it. Yeah, but you know, at this stage, it's good to keep the same ABI for the two compilers, but we could be free to change it, because compilation is done on the Android target, so not on the host. So you know, we are kind of isolated shielded from. So we could do these changes, I think, in the future.
And the performance numbers, that Art is 80% generally more performant than Dalvik, is it for ARC64, or does it also apply to ARM? To 32-bit ARM?
This is in general. It was done, I think, for 32-bit, like in general, Art versus Dalvik. Obviously, these numbers will change a lot depending on the benchmark, whether it will be pure Java or you know, even with native code. But it's roughly to say that it gives a considerable performance improvement. And this is basically due to the fact that Dalvik had mainly a just-in-time compiler, which was not, you know, all the code was not compiled, basically.
Hi.
Hello.
So there are few Dalvik Art properties which we set during platform configuration. Like one is specific to dex2oat heap sizes. So how do you fine-tune those properties based on your device configuration? For example, I have a limited RAM, or because all those dex2oat properties, they trigger the on-device compilation, right? So it has to happen at the target side. So there are few, I mean, these are default properties, but we can fine-tune them, right? Or
I guess it depends on the device. I don't have actually a good answer to this question. Yeah, I think it depends on the amount of memory that you have and the type of garbage collection you are using. Yeah, to be honest, I've not looked into like fine-tuning these numbers.
Okay. Thanks.
What will happen to suspend points when you start aggressive optimizations like inlining? Because from what I understand, as soon as you start doing inlining, there is generally, you may start losing suspend points in the small functions.
Yeah, I mean, there are several ways you use suspend points. So if you use them for profiling, you need also to preserve the information about where you are in the code so that you can map it back. But in practice, for other applications, like for garbage collection or debugging, what you really care is that you hit it soon, that you don't keep executing code for a long time without hitting one of them. So in a way, it's if you're doing lining, you need just to worry about preserving this information, being able to store and being able to recover where you are in the code, but that is it, basically.
Are suspend points inserted automatically, or can programmer also insert them via built-in?
They are inserted automatically. At the moment, they are inserted on backward branches. So if you jump back, you make sure that this in principle can be not backward branches. They are inserted into back edges. So if you really go back into the flow, and also when every method has one, so you basically put them such that you are sure you hit one. But at the moment, they are not particularly well placed in the sense that if you have a loop, for example, of doing 3 iterations, in principle, you could avoid putting them into that loop. We don't do this sort of checks at the moment. So, okay. So if you don't have any other questions, I guess I thank you for listening. Thank you.